Dear friends, hearty welcome to today's session of online problem solving session for JAM aspirants. Today we are having Mahesh T.V with us. He completed his MSc from Pondicherry University and did M.Phil from CUSAT and now doing Ph.D. at IIST Trivandrum in the area of differential geometry. So I welcome Mahesh T.V to this program, and I express my thanks to him for accepting the invitation by us to be a part of this program. And also I welcome all of you to this session and hope that the session will be fruitful to all those who are preparing for JAM.
So first of all, thank you for calling me for such a great program. I express my gratitude to Dr. Vinod Kumar for giving me a chance to present something for the students. Okay, I will present functions of several variables. Mostly I will discuss about functions of 2 or 3 variables. So I plan to discuss the following things. The things I wanted to discuss today is limits, continuity, and partial derivatives and directional derivative, and the differentiability of functions of 2 variable or 3 variable. There are some more things in the syllabus, maxima, minima, and integration also there. I don't think I cannot go for those things because it needs time. Okay. So I may suggest some books for further reading. You can look at these 2 books, A Course in Multivariable Calculus and Analysis by Cropper and Limai, and Calculus on Manifold by Spivak. These are the 2 good books for these subjects. So we will start functions of 2 variable. So what do you mean by functions of 2 variable? A function of the form f from D subset of R2 to R. Such functions are called functions of 2 variable. I am talking about real valued functions. So this f of x comma y is in R, and x comma y belongs to T. So I am talking about function of 2 real valued functions of 2 variable real valued functions. So let me give some simple examples. So f of xy is equal to sum x plus y, where x comma y is coming from R2. Another example you can see f of x comma y is equal to sum sin x plus cos y, etc. So a lot of things we can like that you can construct a lot of examples. Okay, here also x comma y is coming from R2. Okay. So let me give example which motivate this course. I just call it as motivating example. Nothing special, but I just call it as motivating example. So let me consider a triangle. So we all know these things. You just consider a triangle. Yeah, and this is the base, and this one is the height. So we all know what is the area of the triangle. Area is half BH. Okay. So what I will do is I just wanted to consider this area as a function of 2 variable, right? Area is nothing but function of 2 variable B and H. So while this base and height are changing, I will get different areas. So this is one function of 2 variable. Area you can think as a function of 2 variable. Okay. Now I will go for limits of the function. Limit of f of xy at some point x naught y naught. I just wanted to talk this. Okay. So let us recall first limit in the case of single variable. Recall. Okay. So what do you mean by, suppose you have a function f from R to R and x naught is some point in R. What actually mean by this? What you mean by limit x tending to x naught f of x? So here we are considering a point on the line, right? So there is a point, it's called x naught. So two way we can approach this point, either from the right or from the left. Okay. Then we will have the two limits called a left limit and right limit. Left limit. What is that? Limit x tending to x naught minus f of x. I say it is some L1, and I assume this is exist. And another one is right limit. Right limit. This is limit x tending to x naught plus f of x, and this L2. So I also assume this also exists. Then if these two values are equal, if L1 is equal to L2, if L1 is equal to L2, that I call some L, say, then we say the limit at x naught exists. Then we say limit at x naught exists, and we denote that by limit x tending to x naught f of x. So this is the common value L. So this is the way we have understood limit at x naught in for a function from R to R at a point x naught. Now I wanted to look at limit of a function from some D subset of R2 to R. So I wanted to introduce this thing. My aim is this. I wanted to look at limit xy tending to x naught y naught f of xy. I wanted to introduce these things. Okay. Now just consider f is from some D subset of R2 to R. So my D is something that like this. This is my D, and I assume always D as an open subsets. Okay, you just assume D is open. Okay, even if it is not open, also we can define, but I'm talking with the open subsets. And x naught y naught is a point in D. So I consider a point here, x naught y naught. Now I wanted to approach this point. As I see here, I have approached this point x naught from both directions, from right and left. So, but here I don't have such a notion, right or left, because we are in the plane. So here I wanted to approach this point. Approach means I will consider all the curve passing through x naught y naught, and along that curve I will approach the point x naught y naught. So first I will consider some curve. I say this is one curve, and I will take another curve. This may be another curve, and I can take some other curve like this. Okay, like that you can have a different curves. So along that curve, we will approach this point x naught y naught. So I call this curve this as the curve one. One is, so I curve one I will consider this, maybe this blue one you can say the curve one. Now I will look at this value, limit xy tending to x naught y naught along curve 1. This curve 1 means some curve. You in the figure you can consider it as the blue one. And then I will look at this value. Then again I will look at the other value, limit xy tending to x naught y naught along curve 2 f of xy. Okay. So and so on. I will look at all the possible curve passing through x naught y naught, and I will look at the limit x naught y naught along that curve. What do you mean by along that curve? Since you look at here, along each curve I can approach the point from by two ways. I cannot say it is left and right, but still there are two ways, either from the bottom, below and above. I can say from below and above. Trying to say is I wanted to introduce the concept limit x tending to xy tending to x naught y naught f of xy for the function f of from D subset of R2 to R, where D is an open subset and x naught y naught is some point in D. So what I have doing here is I just wanted to generalize the definition in single variable case. What I'm doing is I will consider some point x naught y naught, and I will look at all the curve passing through x naught y naught. Now along each curve I will look at the limit of f of xy at x naught y naught. What do you mean by that limit? So I will look at, suppose I call this blue one is the curve 1. I consider that curve, and along that curve I am approaching the point x naught y naught. I can approach two way to x naught y naught along this curve. So both way I have to get the same value. That is the meaning of this limit exist. Limit xy tending to x naught y naught f of xy along the curve 1 exist means both direction or both manner I have the two way I can approach x naught y naught along the curve blue. Then both has to be exist and both has to be same. Like that I can look at for the each curve passing through x naught y naught. Then if all these values are same, then we will say the limit at x naught y naught exist, and that common value will be denoted by limit xy tending to x naught y naught f of xy. So what I am doing is I have to consider the point x naught y naught. I will look at all the possible path passing through that x naught y naught. Then along that curve I will approach the point x naught y naught, and I will look at the value f of xy, limit xy tending to x naught y naught f of xy along each curve. That I will look at. Then if all those values are same, we will say limit at x naught y naught exist, and that common value will be the limit at x naught y naught, and it will be denoted by this limit xy tending to x naught y naught f of xy. This is the notation. So I will give an example to illustrate this. That will be better. So just look at an example. So f of xy is equal to, I may consider this xy by x square plus y square for xy not equal to 0, 0, and 0 for xy equal to 0, 0. Okay. Now I wanted to look at what you mean, whether this exists or not. F of xy exist or not. This is what I wanted to look at. So what I will do is I will consider one curve. I say it's curve 1. Curve 1. I may call it as curve 1. That is nothing but the line y equal to x. So this one. So I have to consider the curve passing through the point 0, 0. The first one I am considering this line y equal to x. This one y equal to x. And I will look at the limit along this curve. What is limit xy tending to x naught y naught along y equal to x. f of xy. That will be equal to, so I have to substitute y equal to x in this equation. So then that will give limit x comma x tending to 0, 0. Or you can say x tending to 0. This is, if I substitute y equal to x, numerator I will get x square, denominator I will get 2x square. So x square will cancel. So this will be 1 by 2 only. Now I will consider another curve. I say it is curve 2. I just take it as y is equal to 2x, another curve. So this is the curve, something like this. Okay. So this is the y equal to 2x. So again, I will look at this value, limit xy tending to x naught y naught. Here x naught y naught is 0, 0. Sorry, I have to write 0, 0 itself. Yeah, this is 0 and this is also 0. Okay. Yeah, x naught is 0. This is 0, 0. Along the curve, along y equal to 2x f of xy, that I have to look at. This is nothing but limit x comma 2x tending to 0, 0. So if I put y equal to 2x, the numerator I will get 2x square, and denominator I will get 5x square. So it will be nothing but 2 by 5. So what I have approached the point 0, 0 along two curve. One is y equal to x, the another one is y equal to 2x. So each one I am getting different value. While looking the limit along the curve y equal to x, I got 1 by 2. Along the curve y equal to 2x, I got 2 by 5. So both are different. So this limit at 0, 0 does not exist for this function f of xy. So in order to exist this, if I consider any curve, I have to get the same value. But I have considered here two curves. One is the y equal to x, the other one is y equal to 2x, but in both one I got different values. So this limit at xy tending to 0, 0 f of xy does not exist. So limit xy tending to 0, 0 f of xy does not exist. Okay. So similarly, we can, but this definition will not help us to find the limit at some point, because we have to consider all the curve passing through some point, but that is not practically not possible. There are infinitely many curve passing through some points. So this definition help us to say only that limit does not exist. In that cases only it will be useful. Otherwise, it will for finding the limit, it is not going to be useful. So I will define that in a more precise way, that is the epsilon delta definition. That will be little bit useful. Epsilon delta definition. So you have already seen this epsilon delta definition of limit for single variable case, that I have just extend for the two variable case. Okay, let D subset of R2, I consider it as an open subset, is an open, so open, and f from D to R, PF map function, and x naught, y naught be an element in D. Okay. We say limit of f of xy at x naught y naught is L if for all epsilon greater than 0, there exists delta positive such that modulus of f of xy minus L less than epsilon whenever, I will tell you what is this, norm of xy minus x naught y naught less than delta. So what is this norm? Norm is nothing but this one. Norm of xy minus x naught y naught is our usual Euclidean distance, square root of x minus x naught square plus y minus y naught square. Okay, so what actually it means? So we say L is the limit of f at x naught y naught. If for a given epsilon, if I can find some delta such that this condition holds. So what actually this condition says? So f of xy has to be belongs to the interval. F of xy belongs to the interval L minus epsilon, L plus epsilon, whenever xy belongs to the ball B delta of x naught y naught. This is the ball in R2. So ball means nothing but this some x naught y naught is somewhere here, and this is a disk, open disk, not including the boundary or delta radius open disk. So whenever xy belongs to that ball, f of xy has to be lies between L minus epsilon and L plus epsilon. So this is the definition. Then we say L is the limit of f of xy at x naught y naught, and we denote this limit xy tending to x naught y naught is f of xy is equal to L. Okay, this is the notation. Denote. Okay. So this is the more precise way of defining limit of at x naught y naught of f a function f from D to R, where D is a open subset of R2. Okay. Now I may recall something called a sequential definition of limit. So these things you might have seen in the single variable case. So just recall that. This also useful for doing problems. So I just recall this. So f from R to R, and x naught is some point in R. We say L is a limit. L is a limit of f at x naught y naught. Sorry, it's not at x naught y naught. It's single variable case, right? At x naught. Yeah, at x naught. If for any sequence xn converges to x naught, should imply f of xn should converges to L. So this is a single variable case. F from R to R and x naught is a point in R. So we say L is a limit of f at x naught. I wanted to look at this definition in the sequential way. So what is meaning? If for any sequence xn converges to x naught, that should imply f of xn converges to L. In that cases, we say L is the limit of f at x naught. So there you have to consider every sequence xn converges to x naught. So the same definition I can extend for two variable case. So what should be that? So So you have a function f from D subset of R to R, and some x naught, y naught is a element in T. So what we say L is a limit of f at x naught, y naught. We say L is a limit of f at x naught, y naught if for all sequence xn yn converges to x naught, y naught, will imply f of xn yn converges to L. So you have to consider all the sequence xn yn converges to x naught, y naught. Then f of xn yn has to converges to L. Then we say L is the limit of f at x naught, y naught. Okay, this is the sequential way of understanding this definition. So I just wanted to illustrate the previous example using this thing. So I just give it. So you consider the same example what I have discussed earlier. F of xy is equal to xy by x square plus y square for xy not equal to 0, 0 and 0 for xy equal to 0, 0. Okay. Now I just wanted to look at limit at 0, 0. So you consider the sequence. I have taken the sequence xn yn is equal to 1 by n, 1 by n. This will converge us to 0, 0. Okay. As n tending to infinity, 1 by n converges to 0, 0. Now you look at f of xn yn. What you will get? If you substitute f of xn yn, it will be in the numerator I will get 1 by n square. 1 by n square. In the denominator I will get 1 by n square plus 1 by n square, that is 2 by n square. So 2 by n square. This will be nothing but 1 by 2. So f of xn yn converges to 1 by 2 as n tending to infinity. Now if you look at another sequence xn yn, that is equal to some 1 by n, 2 by n. This is again converges to 0, 0 only. But if you look at f of xn yn, what you will get? F of xn yn, that will be in the numerator I will get 2 by n square. So it is 2 by n square in the numerator. And in the denominator what I will get? 1 by n square plus 4 by n square. So it is 5 by n square. So it is 5 by n square. So it will be 2 by 5. So as n tending to infinity, this f of xn yn converges 2 by 5. So but see here, we have a two sequence. One is 1 by n, 1 by n, that is converges to 0, but f of xn yn that converges to 1 by 2. And another sequence is 1 by n, 2 by n, that converges to 0, but f of xn yn converges to 2 by 5. But it says that this it says that what actually it means, you will not find a unique value for such a sequences. So it means f is not continuous at f is the limit at 0, 0 does not exist. It's not continuous. It says that the limit at 0, 0 not exist. So this means limit xy tending to 0, 0 f of xy does not exist. Okay. This is the meaning. Okay. Okay. Now we will see some more examples. Another example I will give you. So f of from R2 to R defined by f of x comma y is equal to sine of xy for xy not equal to 0 0, and this one I called as 1 4 0 0. Okay, I just wanted to look at what is limit. So my aim is to look at this limit xy is to 0 0 f of xy. I wanted to find this. Okay, so I consider some arbitrary sequences x and yn. Consider x and yn which converges to 0 0. Okay, some arbitrary sequence. So if x and yn converges to 0 0, what happened to xn into yn? X and yn, this also converges to 0 as n tends to infinity. Now I may call this xn into yn as some zn. So you just call zn is xn yn. I know this zn converges to 0. So what you know about this sin x? Sin is a function from R to R. If I look at this as function from R to R, that is a continuous function. So what happened to this sin of zn? Sorry. What happened to this sin of zn? This will converge to sin 0 because of the continuity of sign. Reason sin is a continuous function. Okay. So this one is 0, right? This is equal to 0. So what happened to this? If x and yn converges to 0 0, what happened to f of x and yn? That is f of x and yn. That is exactly the sin of zn that converges to 0 as n tends to infinity. So if you take any sequence x and yn converges to 0 0, then f of x and yn converges to 0 as n tends to infinity. That means limit xy tending to 0 0, f of xy is nothing but 0. Okay. So the limit exists at 0 0. That value is 0 only. Now, what do you mean by the continuous function? A function f is said to be continuous at the point. F is said to be continuous. CTS means continuous. I just use the abbreviation. Continuous at some point x0 to y0 means limit xy tending to x0 to y0, f of xy has to be equal to f of x0 y0. That's all. So if this value agrees with the f of x0 y0, then f is a continuous function. So you can observe from here, we got that limit xy tending to 0 0, f of xy is 0. But here this is not equal to f of 0 0, right? This one is not equal to f of 0 0. So this function is not continuous at 0 0. F of 0 0 is 1. But I got a limit xy tending to 0 0, f of xy is 0. Okay. So this function is not continuous at 0 0. Okay. Now I will give another example. I may recall something called a polar coordinate system. Polar coordinate system. So you guys have already studied these things. So if you have a point x comma y here, we can associate a coordinate for that. That is, one is the this distance and the other one is the angle. theta. So that coordinate system is denoted by r comma theta, and r will be always positive, and theta always lies between, you can say, there is minus pi to pi. Okay, so that is the r theta coordinate system. So here x you can represent it by x is equal to r cos theta, and y is equal to r sin theta, and then x square plus y square is r square, and theta you can take as tan inverse y by x. Okay, this is the conversion formula. So I think you have done this in your course, previous course. So I just look at one example, and I will find the limit at some point using this polar coordinate system, conversion. Okay. So I consider the example. F of x comma y is equal to x square y by x square plus y square for xy not equal to 0 0 and 0 for xy equal to 0 0. Okay, so what about the so I wanted to look at limit xy tending to 0 0 f of x comma y. This is the thing I wanted to find. So what do you mean? Yeah, so what I'm going to do is I just using the polar coordinate, I will convert this equation into polar coordinate using the, so I will write f of r comma theta. What is this f of r comma theta? So x I will substitute x equal to r cos theta. So it will give r square cos square theta into, so in the numerator what I will get, x is r cos theta. So x square will becomes r square cos square theta, and y is r sin theta. So totally I have a r cube is there. So it is in the numerator what I will get, r cube cos square theta sin theta, and in the denominator what I will get, x square plus y square, that is r square. So the denominator I will get r square. So it will be nothing but r cos square theta sin theta. So now I just look at modulus of this f of r theta. This I can bounded by r square, because cos square theta and sin square theta both are bounded by 1. So I just use that bound. Then f of r theta modulus of that will be less than or equal to r square. Then what happens if xy tending to 0 0? What happens to r? R will tend to where? So our xy is somewhere here, and r is this. So if xy is approaching to 0, what happened to this r? R is also going to 0. So this one is same as xy tending to 0 0 f of xy will be same as limit r tending to 0 f of r theta, right? Then this, what happened from this equation, what I will get from this equation. So here from this equation what I will get, this limit r tends to theta f of r theta should be is equal to 0. So limit xy tends to 0 0 f of xy exists, and that value is 0 only, because while tending r tending to 0 I will get the right side 0, and the modulus of something is less than or equal to 0 has to be that inside value also has to be 0. So limit r tends to 0 f of r theta has to be 0. Okay, so what I got, limit xy tending to 0 0 f of xy is 0. So that will be equal to, it is in fact equal to f of 0 0. So this function is continuous at 0 0. The given function is continuous at 0 0. Okay. Okay, now let me go to something called a uniform continuity. Uniform. Okay. So you might have seen this thing for single variable case. So just recall what you have done in single variable. So you have a function f from some E subset of R to R, and is said to be uniformly continuous on E. Is said to be uniformly continuous on E for any sequence. If for any sequences for any sequences xn and yn in E such that modulus of xn minus yn tends to 0, we have modulus of f of xn minus f of yn tends to 0. So you consider a function f from E subset of R to R, and that function is said to be uniformly continuous on E if for any sequence, if you consider any two sequence xn and yn in E such that their difference goes to 0, then f of x and yn has to goes to 0. So if you consider any such sequences xn and yn, so that their modulus value xn minus yn modulus value goes to 0, then f of modulus of f of xn minus f of yn has to goes to 0 as n tending to infinity. Then f is said to be uniformly continuous. So whatever the sequence you take, if their difference goes to 0, then f of xn minus f of yn also has to goes to 0. So let's see one example for uniform continuous function for single variable case first. Example, I consider f from R to R defined by f of x is equal to x square. You might have seen this example previous. This function is not uniformly continuous. I just look at this thing using this definition. So I consider two sequences. So one xn I taken as root n, and yn I will taken as root n plus 1. So what happened to modulus of xn minus yn? What happened? This one, modulus of xn minus yn. What is this? Modulus root n minus root n plus 1. So this is nothing but I have used the conjugate multiplicity. Then it will be 1 by root n plus root n plus 1. So as n tending to infinity, this will goes to 0. So this goes to 0 as n tending to infinity. Now you consider f of xn. What you will get? F of xn is f of x is x square. So xn is root n. So f of xn is nothing but n. What about f of yn? That is equal to again n plus 1. Then what happened to this modulus of f of xn minus f of yn? That is equal to 1. This value does not goes to 0. Okay, as it says, we have obtained two sequence xn and yn so that the difference goes to 0, but f of xn and yn is not going to 0, which means f is not uniformly continuous on R. The given f is not uniformly continuous on R. Okay. So the same thing I can use for same definition I can use for the function from R2 to R. So I will return it as a definition. So I consider a function f from D subset of R2 to R is said to be uniformly continuous on D if for any sequences x and yn and a and bn in D such that that norm of x and yn minus a and bn tends to 0 implies modulus f of x and yn minus f of a and bn. This is 0. Okay. So here the norm is nothing but the Euclidean distance. Norm of x and yn minus a and bn is nothing but square root of xn minus an square plus yn minus bn square. Okay. So whenever this value goes to 0, this thing has to goes to 0. Okay. And the same case, here we have discussed with respect to single variable that I have extended for the two variable case. That is all. So you have to consider any two sequences such that the difference goes to 0. Then their f of x and yn also has to be goes to 0. That difference also goes to 0. Then we say f is uniformly continuous on D. Okay. So let me look at some examples. So this is a very simplest example. So you have taken f from R2 to R, and f of x comma y is taken as x plus y. Simplest example I have taken. So now you take some two sequences, arbitrary two sequences you choose, xn and yn. This is one, and another one, and an, bn. Two arbitrary sequences. 2, 3 sequences such that square root of xn minus an square plus yn minus bn square converges to 0. So such a sequence I choose. I choose two arbitrary sequences so that these things happens. Now I will look at what is f of x and yn. What you will get? This is xn plus yn. What is f of a and bn? That is also equal to an plus bn. Now if I look at modulus of f of x and yn minus f of a and bn, that will be modulus xn minus an plus yn minus bn. I just arrange the things so that xn and an comes together and yn and bn comes together. So I can use the triangle inequality. This will be modulus of xn minus an plus modulus of yn minus bn. What you can say about this modulus value and this square root value? I can write this will be less than or equal to 2 times square root of mod xn minus an square plus mod yn minus bn square, because each term is less than or equal to this thing, right? The reason is this. Reason. Can say modulus of xn minus an should be less than or equal to square root of xn minus an square plus yn minus bn square. If you want to understand, just square it both side, then you can get this side xn minus an square. Here this side you will get xn minus an square plus some extra term. So this will be less than or equal to this. Similarly, modulus of yn minus bn also less than or equal to square root of xn minus an square plus yn minus bn square. Okay. So what happens this? Now I know this value is going to 0 as n tending to infinity. So what happened to this value? This also will go into 0, which implies this implies limit n tending to infinity, limit n tending to infinity yeah. Is it visible now? Is it visible?
Yes, sir. It is visible.
Yeah. Okay, fine.
Yes, sir, it is visible.
Okay, fine. Okay. So this will implies limit n tending to infinity modulus of x and yn minus f of a and bn has to be 0, right? Because from this we have assumed these conditions. We have chosen two sequence so that this thing goes to zeros. So I got from here these two values are, this is less than or equal to 2 times of this. As n tends to infinity, this will be 0. So this has to be 0. So what I get, limit n tends to infinity modulus of f of x and yn minus f of a and bn has to be 0, which means f is uniformly continuous. This implies f is uniformly continuous. Okay. Okay. Now I will give an example so that it is not uniformly continuous. So this is just a generalization of the example what you have learned in single variable case. That is the 1 by x, you know, open interval 0, 1, 1 by x is not uniformly continuous. So that function I will generalize for two variable cases. So I will take d as the following. D is this set of all x comma y belongs to R2 such that x comma y belongs to closed interval 0, 1 and this x comma y not equal to 0, 0. So this is my D. What is the D? So you have a square and this point is not there. That is my D. This is my, this entire region, inside portions are also there, but this point is not there. This is my D. Now I define f from D to R. So f I define from D to R. How I define? F of x comma y is equal to 1 by x plus y. So this function I take. Okay. What happened to this function? I wanted to look at whether this is uniformly continuous on D or not. So I will consider two sequences. So I take x and yn. This as the first sequence. This is 1 by n comma 0. And I take a and bn. This is the second sequence. This is 1 by n plus 1 comma 0. Okay. Then what happened to this thing? I wanted to look at whether this value goes to 0. Xn minus an square plus yn minus bn square. What is that? This is nothing but 1 by n minus 1 by n plus 1 whole square. So it will be 1 by n into n plus 1. This value goes to 0 as n tends to infinity, right? Okay. So now I will look at f of x and yn. So what is f of x and yn? That will be, so I have to substitute in this equation. My f of xy is 1 by x plus y. So f of x and yn is 1 by n. So that is nothing but n. What is f of a and bn? F of a and bn is again 1 by n plus 1. That is n. Sorry, n plus 1. Okay. Then modulus f of x and yn minus f of a and bn. This is nothing but 1. This does not goes to 0. So what it says, we have obtained two sequence x and yn and a and bn. This is the first sequence and this is the second sequence. So that their norm means the Euclidean distance goes to 0 as n tends to infinity. And but the modulus value of f of x and minus f of a and bn is not going to 0. It means f is not uniformly continuous on D. So f is not uniformly continuous on D. F is not uniformly continuous on D. Okay. So I can give you a problem. You can try this later. So the problem is this. Just try this later. F of xy is equal to x square plus y square. And this is defined for all R2 to R. Whether this is uniformly continuous or not. Is F is uniformly continuous or not. So you can immediately observe this thing. This is nothing but a generalization of f of x equal to x square. This is the generalization of that function. We have seen f of x equal to x square is not uniformly continuous. We have seen it already, right? Here, yeah. This one, f of x is equal to x square is not uniformly continuous from R to R. This is nothing but a generalization of such a function. F of xy is equal to x square plus y square. It is defined from R2 to R. So you just observe two sequences so that the difference goes to 0, but f of x and yn minus f of a and bn does not goes to 0. Then you can obtain that this is not uniformly continuous. So you need to produce two sequences. Okay. Now I will go for partial derivatives. Partial derivatives. Okay. So what is partial derivatives? Okay, let me define precise. Let D is a subset of R2 and let f from D to R be any function. Be any function. Okay. Now fix some point. Fix some point x naught y naught in D. Okay, and define two sets and define D1. What is D1? I will tell you. This is set of all x belongs to R such that x comma y naught belongs to D. And another set D2. This is set of all y belongs to R such that x naught comma y belongs to D. Okay. So I will look at all those x so that x y naught belongs to D. D is the domain of the function and x naught y naught is a point in D. And I will look at all those y so that x naught y belongs to D. Now I will define the partial derivative as follows. If x naught is a interior point of point of d1, then only I can define the partial derivative of f with respect to x at x0 y0. If x0 is interior point of d1, we define the partial derivative of f. We define the partial derivative of f at partial derivative of f with respect to x. I just wanted to say to of f with respect to x at x0 y0 is defined as the following way. That is I may denote the partial derivative by fx at x0 y0. This is nothing but limit h tends to 0 f of x0 plus h comma y0 minus f of x0 y0 by h. We only make increments on the first variable. Okay. And similarly, I can say if y0 is the interior point of d2, then I can define, we can define fy at x0 y0, that is nothing but limit h tending to 0 f of x0 y0 plus h minus f of x0 y0 by h. This is the partial derivative with respect to y at the point x0 y0. We are looking the partial derivative at a particular point. Okay, at the point x0 y0. So this is the definition. Okay, so we usually denote by this. Another notation we will follow by this, dou f by dou x at x0 y0. This is another notation. Okay, another notation. Okay, now let me go to some examples. Okay. So these two, I will discuss two examples. These two examples are very important. Example. So you consider f from R2 to R defined by f of x comma y is equal to square root of x square plus y square. So I just wanted to look at whether this quantity exists. I wanted to look at whether fx at 0 0 comma fy at 0 0 exist. This is my question. Okay. So what you look at this fx at 0 0. What is that? That is equal to, by definition, limit h tending to 0 f of 0 plus h comma 0 minus f of 0 0 divided by h. Okay, so that will be equal to limit h tending to 0. What is the numerator is f of h comma 0. F of 0 0 is what? That is 0 only, right? Because f of xy is square root of x square plus y square. So that value is 0. So this is f of h comma 0 by h. So this value is nothing but what is f of h comma 0? That is limit h tends to 0 square root of h square by h. So this is equal to limit h tending to 0 modulus of h by h. So this does not exist. Does not exist. Okay. What is the square root of h square? You will get plus or minus h. That is why I put modulus of h. And this value does not exist, because whenever you coming from the right, you will get 1. If you coming from the left, you will get minus 1. Okay. So this does not exist. So what you have seen that fx at 0, 0 does not exist. Similarly, you can compute this value fy at 0, 0. That is also equal to limit h tending to 0 f of 0 comma h minus f of 0, 0 by h. This is also same as limit h tending to 0 square root of h square by h. So this is limit h tending to 0 mod h by h. So this value does not exist. Does not exist. Okay. So what you have observed from this example, we have a function f of xy. So is partial derivative at 0, 0. Both the partial derivative does not exist. But what you can say about this function, this is a very nice function. So it's a continuous function, right? This function is continuous, but even if it is continuous also so what you can observe, continuous functions partial derivative need not exist. Okay, you can write it as a note. So note. Yeah. So continuous function partial derivatives need not exist. Partial derivatives need not exist. Okay. So I wanted to look at whether there is any connection with the continuous function and continuity of the function and the existence of the partial derivative. So we have seen that this function is continuous, but still the partial derivative is not exist. Now I will give an example. The function is not a continuous, but still there the partial derivative will exist. So continuity and partial derivative have no implications. So even if it is continuous, also in that cases partial derivative need not exist. But for the discontinuous function, partial derivative still exist. I will give an example of a discontinuous function, but the partial derivative will exist. So another example. So you take this f of xy is equal to xy by x square plus y square, xy not equal to 0, 0. We have already seen this is not a continuous function. We have seen this function's limit at a 0, 0 does not exist. Not even exist. Yeah. Okay. Now, let me look at what is fx at a 0, 0. What is that? Limit h tends to 0, f of h comma 0 minus f of 0, 0 by h. This value is, what is f of h comma 0? If you substitute here, what happens? Y is 0. So this total value will be 0. And f of 0, 0 is already 0. So you will get here it is 0. Similarly, what happens to this one? F of y of fy of 0, 0. That is again 0, right? Only the difference is you have to take 0 comma h. But still in the numerator xy term is there. So it is 0. But this function we have already seen. This function is not continuous. Not even the limit exists at 0, 0. Yeah, this function is not continuous function, but still the partial derivative at 0, 0 exists. Okay. Now I will give a exercise so that you can do it later. I don't have that much time to do all the problems. So I can define f from R2 to R. You try it later. F of x comma y is equal to mod x plus mod y. So you should find this one. Question is is fx at 0, 0 and fy at 0, 0 exist. Okay. Now I will go for the generalization of partial derivative. It is called directional derivative. I may call it as generalization of partial derivative. Generalization of partial derivatives, or you can say it's called a directional derivatives. Okay. Now I consider that D is a subset of R2, and therefore from D to R be a function, and x0 y0 is a point in D, and let U is some vector I denoted by U1 comma U2 belongs to D, and I cannot say it belongs to D, some vector in R2, you can say. It's a vector in R2, and it's a unit vector. I say it's a unit vector. What is unit vector? U1 square plus U2 square has to be 1. Okay. Now we define the directional derivative of f at x0. The directional derivative of f at x0 in the direction of u is denoted by du f at x0. That will be nothing but limit t tending to 0. This point, this small x0 y0, I will denote by capital X0. This point I denoted by x0. Okay. So du of f at x0 is limit t tending to 0, f of s0 t u minus f of x0 by t. So this is, you can precisely write it as the following. This is t tending to 0, f of x0 plus t u1, comma y0 plus t u2 minus f of x0 y0 by t. So this is the definition of directional derivative of f in the direction of u. U is any unit vector in R2. F is from D to R. D is a subset of R2, and x0 is a point in D, and I am looking the directional derivative at the point capital X0 in the direction of u. Okay. So why it is called generalization of partial derivatives? Suppose you take u as the vector, u is equal to E1. What is that E1? E1 is the vector 1, 0. What happens to D E1 of f at capital X0? What is that? If I looking here, this is nothing but limit t tending to 0, f of x0 plus u1 is 1. So it is x0 plus t, comma y0 plus what is u2? U2 is 0 here, because I am taking u as e1. E1 is the vector 1, 0. So this is f of x0 plus t and y0 minus f of x0 y0 by t. Right? This is by t. What is this? This is nothing but our fx at x0 y0. So the directional derivative of f in the direction of the unit vector e1 is giving the partial derivative with respect to x at x0 y0. Similarly, if you look at the directional derivative de2 of f at x0, e2 is the vector, this will be nothing but fi of x0 y0, where e2 is nothing but this, e2 is 0, 1. So we are looking basically the following. So we have a point where then we will look at the unit circle. This is the unit circle, and this is the point of u1 comma u2. So you are looking the derivative in the direction of u1 comma u2. Similarly, you are looking here the derivative in the direction of 0 comma 1. This is your 0 comma 1. That is your e2. Again, I can look at the derivative in this direction. 1 comma 0 is if the derivative I am looking in this direction, that is getting our partial derivative with respect to x. So if I am looking in this direction, that is nothing but the partial derivative with respect to y. So I will generalize that for any unit vector. So I will look at some unit vector u, that is the u1 comma u2, and I am looking the derivative in that direction. That direction derivative is that is called the directional derivative in the direction of the given vector. Okay, that will be denoted by these things, du of f at x naught. So I wanted to point out some important thing. So I call it as some common mistakes. Common mistake. Okay, what is that? You might have seen this directional derivative in your vector calculus theory. So most of the people will directly suppose you have given some function f, and they are asking you to find the directional derivative. Suppose f is given, f from d subset of R2 to R, and at some point x naught y naught in D, and in some direction u is given as u1 comma u2. Okay, so some direction. So suppose you are asking to find the directional derivative. In our small classes like UG, or people might have done this. Most of the people will discuss this directional derivative with respect to the gradient, right? Del f of x naught y naught dot u1 comma u2. This might have the definition you have seen in your classes, but this is not correct in generally. That is, if you find this, it won't give the directional derivative in generally. There are some condition is needed for f to get this definition. Okay, so what I wanted to say is this directional derivative du of f at x naught y naught need not be equal to del f x naught y naught dot u1 u2. These two are need not be equal in general. There are some certain condition is needed for f. After that only this will be equal. So in general, these two are not equal. So by giving some function, you cannot directly go for this thing del f dot u to find the directional derivative. Okay, I will give you an example so that these two are not equal. So you look at this example. This will be most important. F of x comma y is equal to x square y by x raised to 4 plus y square xy not equal to 0 0, and 0 for xy equal to 0 0. So you just take any arbitrary vector u. U is any arbitrary vector. It's called a u1 comma u2. You wanted to find the directional derivative at some point. Okay, so I will look at the directional derivative at 0 0. So what is this? D uf at 0 0. By definition, this is limit t tending to 0 f of 0 plus tu1, that is tu1, and tu2 minus f of 0 0 by t. But f of 0 0 is 0. So this is nothing but limit t tending to 0. Tu1 is what? So f of tu1, f of tu2, what you just substitute in here. In the numerator, what you will get? T square u1 square and tu2. So totally there is a t cube, right? So t cube u1 square u2. So I will get t cube u1 square u2. In the denominator, what you will get? T raised to 4 u1 raised to 4. Okay. So it will be t raised to 4 u1 raised to 4 and plus y square. What you will get? T square u2 square. So plus t square u2 square and whole divided by t is there. That t I will take here, right? Okay. Now one t will cancel. What will be that? Then the remaining is how many t I can cancel? I can take t square outside from this. This one is plus. Okay, I can take the t square outside. Here also t square is there. So total t cube will cancel. So the remaining is limit t tending to 0 u1 square u2 divided by t cube is gone. Then here remaining t square is there. T square u1 raised to 4 plus u2 square is there. So this will be equal to what? As t tending to 0, this term will cancel. This term will go. So the remaining is, I can write it as like this. If u2 is not equal to 0, this will be equal to this. u1 square by u2. If u2 not equal to 0. If u2 is equal to 0, this total term is 0, right? So it will be 0. If u2 is equal to 0. Okay. So I have started with some arbitrary vector u1 comma u2. So if u2 is equal to 0, I will get the directional derivative as 0. If u2 is not equal to 0, I will get the directional derivative u1 square by u2. Now what is this value? I wanted to look at, so I got d, so this value is nothing but du of f at 0, 0. That I got. Directional derivative of f in the direction of u at 0, 0. Now I wanted to check whether this is equal to, I wanted to check this. I wanted to prove this, right? This is not equal to del f of 0, 0 dot u. This is the thing I wanted to do. Okay. So what is del f of 0, 0? Del f of 0, 0 is nothing but fx 0, 0 comma fy 0, 0, right? So what is fx at 0, 0? Fx at 0, 0 is the directional derivative of f in the direction of E1, right? This is nothing but d E1 f at 0, 0. So what is E1? E1 is 1 comma 0. So here u2 term is what? 0. U is u1 comma u2. In this case, for E1, what is our u2? That is 0, right? So that will come into the second case. So what is your d E1 f of 0, 0? That will be nothing but 0 only. What happened to this one? Fy at 0, 0. This is nothing but directional derivative in the direction E2 of f at 0, 0. That is equal to. So you look at here. Anything is there? Any question or something? Hello? Hello?
Hello,
Yeah.
Mahesh.
Yeah.
Somebody is asking to explain this example once more and ask how the t cube cancel like that in the chat box.
Okay. 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 Just a minute. I just finish it and I will explain once more. Okay.
Okay.
Okay. Then what is fy at 0, 0? That will be d e2 at f at 0, 0. That will be again 0. I will tell you how it comes. Okay. So let's see here. So the function is this one. F of xy is equal to x square y by x raised to 4 plus y square for xy not equal to 0, 0. And for xy at 0, 0, it will be 0. Now I wanted to look at the directional derivative of f in the direction of u at 0, 0. That is this is the notation for that one. Du f at 0, 0. So that will be nothing but limit t tends to 0 f of t u1 t u2 minus f of 0, 0 by t. Okay. Now you look at what is f of t u1 t u2. you have to substitute the value here. So in the numerator, what you will get? T1 t square u1 square. Then why you have to substitute t u2? So total how many t's comes there? T cube. T cube into u1 square into u2. That is in the numerator. T cube into u1 square into u2. Okay. Now in the denominator, what will come? T raised to 4 u1 raised to 4 plus t square u2 square. That is in the denominator, and whole divided by 1 t is there. So there is one t here. That also we have to write. So there is one t is here, whole divided by t. That t is coming here. So this is the total term in the numerator. Divided by t is there. That will come in the denominator. Okay. Now here I have t raised to 4 u1 raised to 4 plus here I have t square u2 square. So the common term what I can take outside, here I have a t square, here I have t raised to 4. So from here I can take outside t square. So in the below term what I will get? T cube it will come t cube here, right? From each term I have taken t square outside. So already one t is there. Total I will get here t cube. And the numerator also one t cube is there. So those two t cube will cancel. So the remaining is u1 square u2 by t square u1 raised to 4 plus u2 square. So if you want, I can write it here. So this will be t cube u1 square u2 whole divided by, I can take a t cube will be there. Here t square u1 raised to 4 plus u2 square. So these two t cube will cancel. Is that okay? Is that okay?
Yeah, they have commented in the chat box. They are okay.
Okay.
Yes.
Yeah. So so finally what I am getting? So this is the term I am having, u1 square u2 by t square u1 raised to 4 plus u2 square. So as t tending to 0, this the first term in the denominator will cancel, but we have to look at this as a cases. Suppose u2 is equal to 0, what will happen? Denominator also I will get a 0 term, but if I put u2 is equal to 0, numerator automatically will go. After that only I have to send the t, I have to use the limit. But so the total term is automatically 0 there. If u2 is equal to 0, I will get 0. If u2 not equal to 0, what I will get? u1 square u2 in the numerator. Denominator I will get u2 square. But one u2 is already there in the numerator, that will cancel. So that is why I will get u1 square by u2. If u2 not equal to 0, I will get u1 square by u2. If u2 is equal to 0, I will get it as 0. Okay. Now I just wanted to prove that these two are not equal. So this is the directional derivative I obtained. Now I will go for the del f at 0, 0. What is del f at 0, 0? Fx at 0, 0, comma fy at 0, 0. So what is fx at 0, 0? Fx at 0, 0 is the directional derivative in the direction of e1. What is e1? e1 is 1, comma 0. So this is the case where u2 is equal to 0. So directional derivative we have already computed, and here u2 term is 0. So fx at 0, 0 is nothing but a 0. That is coming from the second part of the directional derivative. Now if you take fy at 0, 0, what is that is nothing but the directional derivative of f in the direction of e2. What is our e2? E2 is 0, comma 1. Okay. So now you go there, E2 is 0, comma 1. Here U2 term is 1. That is not equal to 0. So it will belongs to the first case. Then there the U1 square by U2 is our directional derivative. What is the U1 here? It is 0. So if I put U1 is equal to 0, this term again becomes 0. That is why Fy at 0, 0 is 0. So I got Fx at 0, 0 is 0 and Fy at 0, 0 is 0. So what is our del f? Del f is 0 only. Yeah, so I got del f at 0, 0 is nothing but 0, comma 0. So del f dot u is again what? Del f at 0, 0 dot u is nothing but 0. This is not equal to our du of f at 0, 0. because du of f at 0, 0 we have already find, that is this thing. But this is not equal to this. So del f at 0, 0, del f at 0, 0 dot u is not equal to du of f at 0, 0. So directional derivative of f in the direction of some vector need not be equal to del f dot u. There are some conditions that I will discuss. So you have, I hope you understand this. Is there any doubt? Is there any question? Okay. Yeah.
Okay, you can continue.
So I wanted to look at the things with the continuity and this. You can observe one more thing. So most of the cases, these kind of functions, if you want to look at whether the limit exists or continuity. So here, both the functions in the numerator, you have a polynomial in x and y. Denominator also, we have a polynomial in x and y. And you have to look at the degree of the polynomials. Here, the numerator, what is the degree? X square into y. So it has to be a 3-degree polynomial in x and y. And the denominator, the highest degree is 4. So the degree of the polynomial in the denominator is higher. So if such a situation comes, such a functions not happen to be a continuous function. So you can directly compute that. You can directly look at the curve like y equal to mx or y equal to x, y equal to 2x. You can substitute that, and along each curve you can look at the limit. The one what we did in the first. The same way we can do, but you can easily observe this kind of problem by looking the degree. So here in the numerator, the degree is 3, and in the denominator, degree is 4. So such functions limit at a 0, 0 not going to be exist. So you can directly compute it. So this function is have the property that this function is not a continuous function, not even a continuous function, but all the directional derivative exists at the point 0, 0. This function is not a continuous, but all the directional derivative exist. So in order to exist at the directional derivative, the function need not be continuous. Okay. So here I just write a note. Function is not continuous, but all the directional derivative exist. All the directional derivative exist. Okay, function is not continuous, but all the directional derivative exist. Okay. Now I wanted to look at the converse. Suppose f is continuous everywhere. Is that implies directional derivative exist? So my question is this. Suppose f is continuous everywhere. Is that implies directional derivative exist? Answer is no. I will give an example. So you should work out this. No. Example is very simple. You can easily do it. I'm not going for the computations. This is the function from R2 to R, and f of xy is equal to mod x plus mod y. You can try this function. Its directional derivative does not exist at 0, 0. In any direction. Whatever the direction you take, it won't exist at 0, 0. So du of f at 0, 0 does not exist for any vector, for any unit vector u, that is equal to u1 comma u2. You just compute it directly. You just use the definition and you can compute it. There is nothing. It's very easy function, and this function is continuous also. So continuity of the function does not imply the existence of the directional derivative, and even if the function is not continuous also, the directional derivative will exist. That also exists in all directions. Okay. So just I wanted to go for the concept called total derivative. So after that we will do some problems. Total derivatives. Okay. So I just recall the concepts what you have learned in the single variable case. So recall. I will just extend that definition for two variable cases. So we need some trick for extension. So f from R to R, we have a point x naught in R. So what do you mean by f dash of x naught? F dash of x naught is nothing but x naught is equal to limit t tending to 0 f of x naught plus t minus f of x naught by t. This is the way we have studied for the single variable case. F dash of x naught is the limiting value. Okay. Now this f dash of x naught is what? It is a real number, right? I call it as some alpha. F dash of x naught is some alpha. I call it as some. This is just notation. This is a real number. Okay. Now I just rewrite this equation as follows. So you look at f of x naught plus t minus f of x naught minus alpha times t divided by t. What is that? That will be f of x naught plus t minus f of x naught by t minus minus alpha, right? Minus alpha. Okay. As t tending to 0, what happened is, as t tending to 0, I will get limit t tending to 0 f of x naught plus t minus f of x naught minus alpha t by I will take mod t only. What will be this? This will be nothing but I have to take mod t here. Then this will be happen to be 0, right? Yeah. So what actually it says? So why it is 0? This first term is nothing but f dash of x naught. I have taken alpha as the f dash of x naught. So here I will get alpha minus alpha. That is why it is getting 0. Okay. So now using this thing, I will rewrite the definition of derivative as follows. So I will define f is differentiable at, I will say, so we say f is differentiable at x naught. We say f from R to R is differentiable at x naught if there exists a real number alpha belongs to R such that limit t tending to 0 f of x naught plus t minus f of x naught minus alpha t by mod t happen to be 0. Suppose there exists a real number alpha such that this equation holds, then we say f is differentiable at x naught and we denote the derivative, and the derivative is alpha, and f dash of x naught is the alpha. So what I'm saying, so I am rewriting the definition. So f from R to R is called differentiable at x naught if there exists a real number alpha such that this equation happen to be 0, that then we say f is differentiable at x naught. Suppose there is a real number alpha so that this holds, then we say f is differentiable at x naught, and that derivative is our alpha, so that f dash of x naught is our alpha. Okay, so you can easily prove that if such a alpha exists, that should be unique. You can prove that alpha will be exist uniquely. Okay, if it exists, it has to be unique, that we can prove. Okay, so using this thing, I will extend the definition as follows. So I have to look at the function from where to where? F from some D subset of R2 to R. Okay, so I will say f is differentiable at x naught. We say f is differentiable at x naught if there exists a pair of vector, I say alpha comma beta in R2 such that the following holds. What should be that? Limit t tending to 0 f of, so I say it's differentiable at x naught y naught, sorry, at x naught y naught. So what is that? The same equation I have to say t tends to 0. I cannot say t tending to 0. 1 minute. Sorry, this is x naught y naught only. So I have to say some h comma k. I don't say t. Okay, h comma k. So I have to look at in the vector. I am talking with in R. Okay, h comma k is tending to 0 0. So that this is x naught plus h comma y naught plus k minus f of x naught y naught minus alpha times h minus beta times k whole divided by square root of h square plus k square. This is our norm of the vector I have to take. Here I have taken modulus of t. The same way I have to take here norm of the vector h comma k. So equal to 0. Okay, this is equal to 0. So what I am saying, f is a function from D subset of R2 to R, and we say f is differentiable at a point x naught y naught if there exists a pair of vector alpha and beta in R2 such that this equation holds. Then the derivative at x naught y naught, it is denoted by df of s naught. Then the derivative is denoted by a derivative at x naught y naught is equal to alpha beta. It is denoted by the following: d f at x naught y naught is equal to our alpha comma beta. Suppose there exists a pair of vector alpha comma beta in R2 so that this equation happens, then we say f is differentiable at x naught y naught and the derivative at x naught y naught is denoted by alpha comma beta. df of x naught y naught is our alpha comma beta. Okay, this number is the derivative alpha beta. Okay, now I wanted to observe what is this alpha beta for the function. Suppose f is differentiable, then this limit exists means what? I should approach 0 0 along all possible path, right? Then I have to get the limit value should be 0. Suppose I am approaching 0 0 along x-axis. What happens? If I am approaching 0 0 along x-axis, in that cases y term has to be 0. So k has to be 0, right? So what should I will get? Suppose I am looking along x-axis. along x axis. What happens? So there y is always 0, right? Y is always 0. Okay. Then what happens to this value? So I have to look at limit hk tending to 0, 0 along x-axis f of x naught plus h will be there, correct? X naught plus h, y naught plus k is 0, right? So it is y naught. So because I am looking along the x-axis, and this one is f of x naught y naught. K term will not be there. K has to be 0. Then minus alpha h will be there. Minus alpha h whole divided by root of h square by, that will be turn out to be mod h. Okay. So k term is not there. So root of h square will come. That is mod h. So what is this value? This is equal to 0, right? So all direction. So what I am saying, suppose this limit exists, this is exist that we have assumed, then you have to look at all possible path, or if you look at in every path, this limit has to be 0. So I look at along the x-axis, so again it has to be 0. So it means what? By this equation, what actually it means? It means the partial alpha is nothing but partial derivative of f with respect to x at x naught y naught. So this implies, what is alpha? Alpha is equal to fx at x naught y naught. Similarly, okay, who is reached here? 1 minute. Okay. Okay, so what you got, alpha is equal to partial derivative of f at ax at the point x naught y naught. Similarly, you can find beta. Beta again, you have to look at along the y axis. Then you will get beta is nothing but the partial derivative with respect to. So beta is nothing but partial derivative with respect to x naught y naught, with respect to y at x naught y naught. So same way you can do that. So you have to look at along the path y axis. So you will get beta. So what actually you are getting, suppose f is differentiable, then df at x naught y naught is nothing but, suppose f is differentiable, then you will get df at x naught y naught. Suppose f is differentiable, then df at x naught y naught is equal to del f x naught. So this is our alpha beta, right? Alpha is fx at x naught y naught, and f beta is fy at x naught y naught. So if f is differentiable, then the derivative of f at x naught y naught is nothing but del f at x naught y naught. Okay. So you get df at x naught y naught is equal to del f at x naught y naught. Okay. So now I wanted to. So what you can immediately observe from this thing? Suppose f is differentiable. That means there is a alpha and beta, so that this equation holds. Okay. Then we automatically got that the partial derivative at x naught y naught exists. That is what this says. Partial derivative exists. Alpha is fx at x naught y naught, and beta is fy at x naught y naught. So if f is differentiable, then the partial derivative at that particular point will exist. But now I wanted to look at the converse. Suppose the partial derivative exists at some particular point. Is that implies f is differentiable? So the answer is no. So before going for that, I just wanted to point out some properties of the differentiable functions. These are the same as of the single variable case. So I just point out the properties of partial differentiable functions. Properties. So the first one is, these are the very important one. So you just keep these properties in your mind. So first one is, every differentiable function has to be continuous. Every differentiable function are continuous. Okay, all differentiable functions are continuous. And the second one, what happened to this? Every differentiable functions are continuous. And the second one I will tell you, continuous at that point where it is differentiable at that point. Okay, so I can say it's at that point continuous. So at the corresponding point. At that point, okay, where it is differentiable, there it will be continuous. Okay, then the second is, these are the two important one. Suppose f is differentiable. So if f from D to R is differentiable, at x naught y naught, then all directional derivative will exist. Directional derivative exist at x naught y naught. That is, this quantity will exist du of f at x naught y naught exist, and du of f at x naught y naught should be equal to del f at x naught y naught dot u. Okay, so this is what I wanted to point out. So if the function is differentiable, then this thing happens. Du of f at x naught y naught is equal to del f of x naught y naught dot u. Okay. Next I wanted to say is the sufficient condition for existence of the differentiability. Sufficient condition is the following. So what is the sufficient condition? Suppose all the partial derivative exist and it is exist in the small neighborhood, continuous in the small neighborhood of the point, then f has to be differentiable. So f from D to R be such that both fx and fy exist. Be such that both fx and fy exist on some neighborhood. On some neighborhood, I say D intersection some ball P delta of x naught y naught. Okay, some neighborhood I will say for some delta greater than 0. Some delta positive. And if one of them is continuous, and if one of them is continuous, one of them is continuous, then f is differentiable at x naught. F is differentiable at x naught, y naught. So what I wanted to say, f from D subset of R2, D is some subset of R2. Subset of R2. Okay. So f from D subset of R2 to R B is such that both partial derivative fx and fy exist on some neighborhood of x naught y naught. You take the x naught y naught is a point in D. You these function fx and fy exist in that small neighborhood, and one of them is continuous. No need to be both are continuous. One of them is continuous in that neighborhood. Then f is differentiable at x naught y naught. This is the sufficient condition for f is differentiable at a point x naught y naught. Okay. So converse of this need not be correct. Suppose f is differentiable at some point, then automatically we can say at that point the partial derivative will exist, but it need not be true that the partial derivative is continuous in small neighborhood. It need not be true that it's not even exist in the small neighborhood. I will give an example. I don't have space. I can give some example somewhere here. I just simply write here. Okay. So you can work out that. That may be better. F of xy is equal to mod xy. If you take this function, you can say that the derivative df of 0, 0 will be 0. This will be or 0, 0. You can say, you can find this, and is both the partial derivative will exist. Fx at 0, 0 will exist. Fx at so both these thing will exist. Fx at 0, 0 exist. Fy at 0, 0 exist. But fx at 0 comma some y naught, this won't exist. So that means if you look at some place, if you look at this is your point 0, 0, you can prove that on this line partial derivative with respect to x does not exist except for the point 0, 0. If you remove this point 0, 0, all other point this does not exist. This one does not exist. Okay. Similarly, partial derivative with respect to y does not exist on this x-axis other than the point 0. Okay, only at 0, 0 it will exist, or other point it does not exist. Similarly for fx here. So whatever the neighborhood you take for 0, in that neighborhood automatically the point will come so that the partial derivative does not exist. But what you have seen, f is differentiable, its derivative is 0, 0, both the partial derivative exist, but partial derivative not happen to be continuous in the small neighborhood of, not even exist in the small neighborhood. Whatever the neighborhood you take at 0, 0, you can have a point of x-axis and y-axis. So fx is not exist on the y-axis, fy is not exist on the x-axis. So that you can easily observe. You can just find out these things. You just compute. I'm not going for those things. Now I just wanted to do some problems. So already 4 is crossed. So what about my time?
You can take 10 to 15 minutes. See, students may have short of that data, so you can go for. You can do explain 1 or 2 problems, I think.
Okay. Okay. So this one will be very simple. If somebody can answer it, that will be better. If somebody can answer this thing, that will be better. Very, very easy question. Do you able to see this? Any comment or anyone wanted to answer this question? It's very easy. Otherwise, I can do. No comment.
Hello.
Yeah.
Sir, we can use the identity.
What should be your answer? You have done, or you are? You just ask me what I can do. Tell me.
Hello.
Yeah.
Root of x minus y minus 2 into root
Yeah.
of x minus y plus 2 is
Yeah.
equal to x minus y minus 4.
Yeah. Yes.
So we can cancel and we can
Yeah.
easily
Yeah.
take
Yeah.
less.
Yes. Yes. Or you can just convert it as a single variable. That will be better. Okay. You just
Okay.
take x minus y as some z. Okay.
Okay.
So you may take x minus y is equal to some z. So what happened to this thing? Xy tending to 2 comma minus 2, right? So x minus y will goes to 4. So z will goes to 4. As x comma y goes to 2 comma minus 2, z will goes to 4. Then now this equation you can convert it as like root z minus 2 by z minus 4. So this will be same as root z minus 2 divided by root z plus 2 into root z minus 2, right? So I have used a minus a minus b into a plus b is a square minus b square. So those things. So you can cancel the numerator is root z minus 2, and the denominator also root z minus 2 is both will cancel. Then the remaining is 1 by root z plus 2. Okay. So as z tending to 4, what you will get? 1 by 2 plus 2. Root 4 will come, that is 2. So 1 by 2 plus 2 will come, that is 1 by 4. So answer is 1 by. So limit z tending to 4, root z minus 2 by z minus 4, you will get 1 by 4. So 1 by 4 is the answer. This is very simple. Okay. So now, yeah, I just this also you can do similarly. I will do some different question that will be better. This all are, we have done lot of examples. This will be of same kind. You can directly just go for the definition of partial derivative and you can do. So I will do some different questions. That will be fine. Yeah. What you somebody can tell this answer immediately. Okay. No need to look at any results. Can someone tell the answer? Is it visible?
Yes.
Yeah.
Yes.
So can someone can tell these things? It is very simple. This is only theory. This just we have explained these things. So what about if f
Sir,
is differential? Yeah. Tell me.
sir,
Yeah.
sir,
Yeah.
option A is correct.
Yeah. Okay. Any other option? Any other option is correct?
Option C.
No. You have to be very concentrated. Just look at once more. Yeah. First option is correct. If suppose a function is differentiable, then all the directional derivative of f at exists at 0, 0. That is the property 2. I have said that property. Then yeah.
Many of them are commenting that A and D are correct in their chat box.
Yeah. Yes, that is correct. That's all. Okay. A and D. There is nothing. This if the partial derivative exists and are all continuous, then f is differentiable at 0, 0. So the first option is saying that f is differentiable at 0, 0, then all the directional derivative will exist. Then the second option, I have given an example. If all the directional derivative of f at x 0, 0, then f is differentiable. That is need not be correct. So I have given an example in which f is not continuous, and but all the directional derivative exist. I have given one example. For that example, f is not continuous, but all the directional derivative exist. So for that option, b and c will cancel. You can take that as the counter example for that one. A and D are correct. these are the properties I have mentioned. Okay. Yeah, this one also I can try. So this one you can directly look at. So you just see this one. Yeah. So you have a fxy is given. So first you wanted to look at fx at 0 comma y. What is that? So you wanted to look at the partial derivative at 0 0. Higher order derivative, second order derivative you have to look at. So first you look at fx at 0 comma y. What is that? By definition, this is limit h tending to 0 f of hy minus f of 0 comma y divided by h. So you take y as some constant, right? Y as some fixed value. So you are taking derivative with respect to x, first order. Okay. Now, what is this f of hy? If you substitute here, what you will get? This will be limit h tending to 0. This is h square y h minus y divided by h square plus y square whole divided by h. So that h I will multiply here. So what is f of 0 comma y? That is 0, right? If you put x is equal to 0 in the numerator, the term, all the term will vanish. So this will be the term. So now one h is here, one h square is there. So I can just cancel that. Then remaining is this limit h tending to 0 h 1 minute. Yeah, what is that? H square, correct? Yeah. So hy divided by h square plus y square. So as h tends to 0, denominator what you will get? Y square. What about the numerator? You will get 0. So this quantity is 0, right? So fx at 0 comma y you will get 0. Now again you have to take the derivative with respect to y, but this function is a 0 function. Again you are taking derivative with respect to y, what will happen? You will get a 0 only. So what about partial derivative of this, or derivative? You can say it is derivative itself because it's a function of y alone now. So what about fy fx 0y? This is 0 only, right? Because this is a 0 function. So whatever y you take, you will get a 0 only. Now it's a function of y alone. Again you take the derivative with respect to y, so you will get a 0 only. Okay. So fx fy at 0 0, what you will get? So you fy fx at 0 0 means, what is that? That is nothing but 0 only. Okay. Now you again go for the other one. Fy at x comma 0. Fy at x comma 0. What is that? By definition, limit h tending to 0 f of s comma h minus f of x comma 0 divided by h. So you look at here, f of x comma 0, what will happen? Again in the numerator y term is there. So y is 0 here, so that term will go. Now f of x comma h you have to look at. So here x square will come. Yeah, this will be limit h tending to 0 x square h minus into x minus h by h by h square plus h square whole divided by h. Okay. So what I did is I just substitute x comma h. Y is h. So here 1 minute, I have done some mistake. Yes, oh, here x square is there, right? X square plus h square. Okay. So divided by h. Now this is whole divided by h. So this term will come in the denominator. There is one more h that will cancel. So this will be same as limit h tending to 0 x square into x minus h by x square plus h square. So as h tends to 0, what happens? This the denominator I will get x square. Numerator again I will get x cube. So x cube by x square will come. That is nothing but x. So fy at x comma 0 I will get x. So that is a function of x alone. Now again I have to take the derivative with respect to x. So what happens? If I look at fx fy x comma 0, right? This is a function. So I am taking the derivative of this with respect to x. So I will get 1. So this is, so what about this value? Fx fy at 0, 0. That is nothing but 1. So fx fy at 0, 0 I will get. So this quantity I will get 1. This quantity I will get a 0. So 1 minus 0, the answer is 1. Is that okay? Any doubt?
Yes.
Fine. Understood? Yeah. Okay. So you can tell this question also immediate. Nothing is there. It's very simple. After that, I can finish it. So already crossed the time now.
Okay.
Yeah, this one, this one. This one somebody can tell. So what about dou f by dou x? Just compute the partial derivative. What is that? So you first compute dou f by dou x. So I can write it. Dou f by dou x is what? This is equal to x square plus y square into, I just use the quotient rule, into 2xy uh, minus x square y into 2x divided by, sorry, divided by x square plus y square whole square. So this will be, you can just multiply inside, what you will get, 2x cube y. So that term is there. This, the second term is minus 2x cube y. If I multiply inside 2x cube y, that will cancel. Then the remaining is 2x square y square. Sorry. Yeah. Sorry, 1 minute. So some mistake happened. No, x square y into 2xy. Okay. So if you multiply inside, what I went, 2x cube y, that will be cancelled there. Now I have, yeah, okay, 2x y cube will come, right? Is that correct? So y into 2x y. Sorry, yeah, it's correct only. 2xy is there, right? Square y into 2x. That is correct only. Okay. So you will get 2x cube y, 2x cube y, that is cancelling. Then 2xy square divided by, sorry, 2xy cube divided by square plus whole square. I have done some mistake. Into 2xy. Is that correct? X square y into 1 minute.
Yes.
Yeah. Okay. Sorry, any mistake happened. Right? Okay, then what can you say about the boundedness? Tell me. Okay, it's fine. So this is the derivative you will get. Then how do we look at the boundedness? If this function is bounded, so what about f? F is bounded or not? Suppose you look at the sequence n comma n. Okay, you look at the sequence n comma n. Then what happens f of n comma n? What is that? That will be n cube divided by 2n square. So that is n by 2. Okay, where this sequence goes n comma n, that is going to infinity, right? Infinity, as n tending to infinity. So then what happens to this one f of n comma n? That is also going to infinity. So what you can say about the boundedness now? So along the line y equal to x, if you look at the sequence n comma n, as it goes to infinity, function value also going to infinity. So what do you mean by the boundedness then? Is f is bounded or not?
F is not bounded.
Yeah, f is unbounded. So f is unbounded. Now you look at the partial derivative. So partial derivative you have computed this one, dou f by dou x is equal to this. Is that implies now what you can say about that? Yeah.
We have used the same idea, right?
What?
We can use the same idea, right? Y is equal to x line and sequence.
Is that correct? What about the degree in the numerator and the denominator?
We
Both
4.
the cases 4. Numerator is 4
4.
and denominator also 4.
Yes, yes, correct.
So whatever the thing you have using, that will be cancelled.
Yeah, correct.
So this function has to be bounded. You can prove that. You can just using some inequality you can do that. One thing I can tell you is that okay, you just put it as in this way. This you can write it as 2xy by x square plus y square into y square by x square plus y square. Is it fine?
Yeah, fine.
Yeah. What about the second one? This is bounded by 1. Am I right or not?
Y square by x square, about by 1, correct.
Yeah, this one is bounded by 1. So I can write this is less than or equal to 2xy by x square plus y square. Okay.
Yes.
Now you use the AMGM inequality. What is AMGM inequality? Square root of AB is less than or equal to A plus B by 2. This is the AMGM inequality, right?
Yes.
So you take A as x square, B as y square. So what happens? X square y square is less than or equal to x square plus y square by 2. Okay. So what is the square root of x square y square? That is xy.
Yes.
So you can write 2 times xy is less than or equal to x square plus y square.
Yes.
Again, you divide by x square plus y square. So this quantity is less than or equal to 1.
Yes, correct.
So you understand?
Yeah, understood.
Yeah. So what you got? Dou f by dou x is bounded.
Unbounded. Bounded.
Bounded. F is unbounded.
Bounded.
Okay. So is that time goes now? So one more thing is very simple, and we will finish here. I don't want to go much more. Uh, okay. So this is the function you look at. The given that the directional derivative at 0, 0 exists along the direction cos alpha I plus sin alpha j. So they are asking the value of cot alpha. Okay. So you just write the u. What is your u? You wanted to look at the directional derivative. So u is cos alpha sin alpha. Okay. Now what is du of f at 0, 0? They have told that it exists. So by definition, what is this? This is limit t tending to 0 f of t cos alpha t sin alpha minus f of 0, 0 divided by t. Okay, because u1 is cos alpha, u2 is sin alpha. Okay, and at 0, 0 we are evaluating. Okay, so this is limit t tending to 0. What is f of t alpha? F of 0, 0 is what? In that case, y is 0. So it is given that function is 0. So f of 0, 0 is 0 only. Now f of t cos alpha t sin alpha is what? You substitute here. Then you will get 1 cot alpha whole square by t. Okay. Hello. Is that okay?
Yeah, okay, fine.
Okay. Then now tell me what is cot alpha. It is given that this value exists. When it will be exist? What is the possibility? You just observe it. When this value can exist? Limit t tends to 0, 1 plus cot alpha square by t. When it can exist? When it can exist? Huh? Suppose numerator is some finite value is other than 0. Is it exist? Suppose it is some value, some k in the numerator. Limit t tends to 0, k by t exist or not? Does not exist, right? 1 by t will goes to infinity as t tends to 0. So whatever the value coming in the numerator, if it is other than 0, this value does not exist. So the only possible value of existence is numerator has to be 0. So 1 plus cot alpha has to be 0. So cot alpha has to be minus 1. Do you understand that?
Yeah, somebody answered in the chat box. Cot alpha equal to -1.
Yeah. Okay, it's fine. Then I will stop here. There are a lot of questions, but still, you please try these questions. They are all similar kind of question what we have discussed. Yeah.
Okay.
Yeah.
So thank you, Mahesh, for being with us. I think you can share these questions with our students so
Yeah.
that they can okay. Now
Yeah.
the time for asking to make your comments and questions. You can now turn out your presentation, and the students are ready to ask their doubts and.
Sir, the class was really effective, really informative class, sir. And thank you for your effort. We have already studied it in our syllabus, but you have explained in some different ways, and that was really motivating. Thank you so much, sir. Thank you for your effort.
Sir,
Yeah.
Yes.
thank you so much, sir, for such an effective class. It's very rare to get classes like this on functions of several variables. So thank you so much for your effort, and your notes were very good, sir, while explaining.
Yeah.
Okay.
Thank you,
Thank you,
Vinod, sir, for
Ramya.
arranging this class.
Yeah. Thank you, Ramya. Anyone
Yes, sir.
else?
Thank you, sir.
Okay, I think we will, it is better to wind up here now. So I express my sincere thanks and gratitude to Mahesh for being with us. Expect that he will cooperate with us in future too. And we will meet again on the next Sunday with another person on continuity and differentiability. So till then, bye now. Okay, thank you.
Okay.
So,
Yeah. So thank you. Thank you for giving me a opportunity to discuss with the students. This is very, I feel very happy to discuss things with the students. So I am, once again, I thank you, Vinod sir, for giving me a great opportunity. Thank you. Thank you very much.
we can, yeah, Mahesh, we can think about continuation of one more session on these topics. I think there will be more problems from this side. So
Yeah,
I
yeah,
think we can arrange in future one more class on this type,
yeah,
this
yeah,
type of
yes. Yeah,
things.
I am
Okay.
ready to do that. Okay. I am very happy to do that.
Many of the many
Yeah.
of the students are commenting in box. I think you have seen it.
Yeah, yes, yes.
So
Yes.
somebody is asking for to have a class only for problems.
Okay.
So I
Yeah.
think we can.
Yeah.
Okay.
Okay.
So here, thank you all, thank you all. Our next session will be on the next Sunday. So we can wind up now. Thank you all.